10.1 is on sequences. So a sequence is a function whose domain is a set of positive integers. So 1, 2, 3, etc. So basically, it's an equation where you put in 1, then you put in 2, then you put in 3, and you have a pattern that results. And so there can be geometric sequences and arithmetic sequences, meaning in this case, you're adding 3 each time, but in other cases, you might multiply by something each time, like 2 in this case. There could be other sequences too that follow different patterns. This is like 1 being the input, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Again, the input are the integers that are positive. So in this example here, 8, 11, 14, you can see that there's a consistent common difference of 3. You're adding 3 each time. And so there's some notation that I want us to be comfortable with, and that is we have A, it's because it's arithmetic. A sub 1 is your first term, so 8. A sub 2 is the 11, A sub 3, the 14, A sub 4, the 17, etc. The idea here is that if your first term is 8, you can rewrite the others as your first term plus some difference. Now you only have 1 difference of 3 by your second term. You have 2 differences of 3 for your third term, here and here. 3 differences of 3 by your fourth term. 1 difference of 3, 2 differences of 3, 3 differences of 3 by your fourth term. And so you can generalize this for any term. For example, for A sub 10 or A sub 100 by always doing 1 less than the term number times the number of differences plus that initial value. So if I wanted A sub 10, I could compute it by saying it's the initial term 8 plus 9 of my differences of 3, giving me a value of 35, which you can see if I keep adding 3, my 10th one will be 35. And so to make it more generic, instead of saying 9, I'm going to have 1 less than the term number. So n is the term number. 1 less is how many of the differences you'd have when you start at your initial starting point. So you can have the general formula if you are allowed a note card on a test. This might be something you'd want to put on a note card. It's your first term plus your term number minus 1 times the number of differences. Sometimes people like putting the D in front because then it makes the distributive property a little more obvious. So you can see here, this is a sequence that we have dealt with, actually the same one as we have up here. Common difference being 3 and the starting being 8. So if I wanted to find the value of A sub 70, I could say 8, the initial, plus 69, the 70 minus 1, the n minus 1, 70 minus 1, 69 of my differences of 3. Follow order of operations, do your multiplication and then your addition, and you'll get the 70th term's value. You can also plug it into the formula, the generic formula, which if you, for any term number, and this is the expanded form, from the starting point, this would be a simplified version of it, once the distributive property has happened and combining of like terms. So either way works. You can see same answer. One thing that's kind of nice about this is some people actually write the generic like this, the common difference, and then what is needed when you're to get your correct starting value. So when your first term is 1, your n is 1, you'd have 3 plus what in order to start at that 8? Well, plus 5. So that's another way sometimes we think about writing the generic equation. Essentially, it's A sub 1, and then the D times N, and then minus 1 times the D, and then combining like terms. So here's another generic equation, and so finding the first couple terms, and this one asks for the first 4 terms, you just plug in your term number, your n, 1 wherever there's an n. So sub 1, a sub 1, the first term is 2 times 1 minus 3, again following order of operations. And what you'll see is that your sequence would be -1, 1, 3, 5, the common difference being 2, and the -3 allows you to start at that -1, which is our starting value. So there's also a shortcut. Once you find the first one, if you see the 2, you can just add 2, because that's going to be the common difference, because that's how much it's affected by the term number. Find a sub 3 and a sub 4 for this example. Again, just plugging it in for the n's. This was just to review some rules of exponents. -1 to a third would be -1, 3 squared would be 9, a negative to a positive, however, would be positive, and 4 squared is 16. Determine the general term. That means what is your a sub n? Basically, what's the equation so that you can put in any term, so it's generalized for any term. Find the common difference to find your d, and find your starting a sub 1. So a sub 1 is 2, your common difference is 5. Plug it in. You can leave it like this. You can also distribute and combine like terms and write it in this format. Determine the general term for the following sequence. So again, you're looking for your common difference, 7, your starting point, 3, and your n minus 1, distribute, combine like terms. Same thing here. Difference here, though, is it's going down, so it's a -2. Make sure you distribute the negative. Combine like terms. This one's a little bit different. You might not be able to as easily determine the difference. You might see that there's these 3's up here, but it doesn't follow consistently. But if you rewrite this, maybe you can rewrite this with a 3. And it's 3 over 6. And then you would have 4, 5, 6, 7, and 3's on the top. Oh, this is 3 over 3, so it does match the pattern, which I have over here. Another option, I've had students convert it to decimals, but it's not a consistent thing, so you don't really get your D from that. So this is where it's, maybe not so easy to figure out a D because it's not arithmetic, but what you can do is find the difference for the numerator and for the denominator separately. And so there is no difference, so it's just 0, so it's just always a 3 on the numerator, and the denominator is affected by the term. It goes from 3 for the first term, 4 for the second term, etc. And so the difference is 1 between all of the denominators, the 3, the 4, the 5, 6, 7, and your starting is 3. So 3 plus n minus 1 times 1. Distribute, combine like terms, and you'll get your equation that will give you the generic value for the denominator. So you've got your numerator over your denominator. So again, treat the numerator and denominator separately, and you'll be able to get the terms. We also have this thing called a recursive formula, and that's where you take a prior term. So you go backwards, that's the recursive aspect, and then you add in the common difference. So that requires some other information to be given to you. So if you are told here a sub n equals a sub n minus 1 plus 5, it's saying your prior term, because that's 1 less your term minus 1, the prior term, plus 5. So you're going to have a consistent adding of 5 from the prior term. So you have a sub 1 given to you, and you can only use this formula when your term number is greater than or equal to 2, because you've got to have positive integers as your counting numbers. So 1, 2, 3, I mean the smallest term is 1, but you need your first one to be given to you so that you can find the next one, because you always have to do 1 less. So this is kind of just required for recursive formulas, it's often also written as n greater than 1. But again, since they're counting 1, 2, 3, it also could be written n greater than or equal to 2. So you take your prior term. So again, your term minus 1, so that ends up being a sub 1, which is the prior term. Your a sub 1 was 2, and you add 5. Then you have your 3, so 3 minus 1 would be 2, so that's your prior term plus 5, so 7 plus 5 is 12. So you always need to do the prior one. So it makes it harder to find a nth one, like the 35th one, because you'd need to know what the 34th value is. So there's a little bit about it. There's more on sequences in section 10.3. But essentially, there's the explicit, is your first term, term minus 1, that quantity times your difference, and the explicit formula, which is a prior term plus your common difference.